All right, so today we're going to talk about how we can find displacement from the area under a velocity versus time graph. It's going to be important when we do these problems that we follow a physics problem-solving format. And understand that we're going to go through quite a few steps, even though the problems we're doing right now are very basic. But by going through these steps on the more basic ones, when you run into more challenging problems, it's going to support you and give you more ways to solve the problem. In this scenario, we're going to assume that we have a blinky car from like the beginning of the year. And we're going to say that the blinky car was moving at a constant velocity of 12 centimeters per second for 7 seconds. So first we're going to draw a picture of the situation. So I drew my picture of my blinky car. I'm going to define the system with a dotted line. Notice we've marked where the 0 meter position is and that it's moving in a positive direction. Now we're going to use this to solve the displacement by using the area and the velocity versus time graph. But just as a quick reminder, our position versus time graph for this one would have looked like, it would have been a constant positive velocity, right? That's not true at all. It would have been a constant positive velocity that looked like this, right? And then what about the velocity versus time graph? Well, if we knew that it moved at exactly 12 centimeters per second, now I have to label my axes and put units and values where I know it, and the final clock reading looks like it's 7 seconds. Sawyer, what's the shape of that graph? What's the area of this? What shape is this? It's a rectangle. So if we have a rectangle, we'd say the area of a rectangle is height times base. In this case, the height is the initial velocity and the base is our change in time. In this case, the height, or our initial velocity, is 12 centimeters per second and our base is 7 seconds. And those of us who remember our math facts from 4th grade, 7 times 12 is, you're right, it's 84. And let's take a look at the units. We have centimeter per second times seconds. What cancels out? Second. Which leaves us with just centimeters, which is, oh, I forgot to write that this is the displacement. Is the displacement. Now this is a sloppy mess. I should have built this down here maybe. Oh, and we were supposed to write down what we were supposed to find. So what did we do up here? Check marks as we go. We drew a picture of the situation, identifying position 0 and what direction is positive. We sketched out a velocity versus time graph, which requires labeling the axes, putting quantities in when we know them, and then finding the area of that, writing down the given information, and what we're supposed to find. Start with a general equation, fill in what you know, solve, box your answer. So, what if something was not moving at a constant velocity though? What if something was slowing down or speeding up? In this second scenario, I have picked a wave runner or sea-doo or jet ski or whatever. So you got a person riding on the lake, and the way these things work, for those of you who have not ridden on them, when you take your hand off the gas, you just immediately start slowing to a stop. So, what if we assume that this thing starts going 15 meters per second? You're going super fast, but you slow to a stop in, say, 6 seconds. Well, if we mark our starting position as 0 and we're moving in a positive direction, what would the shape of our velocity versus time graph be? Sometimes it's helpful to consider what the position versus time graph would be. If you're moving in a positive direction but slowing down, that would be like that. So we've got a decreasing positive slope or a decreasing positive velocity. So I used my ABCs to figure that out. Do we know the starting velocity? How fast was it going at the beginning? What'll help here, how fast was it going at the beginning? Yeah, so our y-intercept is going to be 15 meters per second. And do we know the final clock reading? 6 seconds. Now we need to find the displacement. How do we find the displacement? Well, it's the area under our velocity versus time graph. But Macy, what shape do we have here?
Oh, a triangle.
A triangle. So the area of the triangle we know is 1/2 height times base. We know that the area of the triangle is the displacement, and in this case, the height of our triangle is our starting velocity, And the base of our triangle is our change in time. Addison, what was our starting velocity again?
15 meters.
Thank you for including the units. And our change in time was 6 seconds. So, I need to do some mental math now. What's half of 6? 3, and 3 times 15 is? 45. And let's take a look at the units. We have meters per second times seconds, which is?
So
Seconds cancel out, so we just end up with meters, which is our displacement. Are meters the right kind of units for displacement? That's one of the reasons we want to carry these units out. So we now have figured out how to find the area under a velocity versus time graph for both a constant velocity problem and an object that is accelerating.